go up the slope here, that's all Catoctin Greenstone. It's metamorphosed basalt, metamorphosed to a low grade, and it actually is greenish. So you can see why it's called greenstone. Below here, and to the south, if you continue, it's all, and that's about 700 million years old. South of here, it's 400 million years older. It's about 1100 million years old, which is no real problem. That's as expected. I mean, this is the exposed gneiss, and the basalt came in over it, flowed over the top of it. No problem. Except that right here, you find alternating layers of greenstone and gneiss, and that shouldn't happen. As a matter of fact, none of the geological descriptions I've seen of the contact mention that little fact. However, yeah, that's a good. This is the greenstone.
Hold it up for this camera. Up, yeah. Well, that's too far up. Like right. That's good.
Okay, this is the Catoctin Greenstone, and you can see where it got its name. That's a mixture of green amphibole and chlorite, which is an indication of green schist low-grade metamorphism. And it came as basalt, flood basalts, covering thousands of square miles all up and down the east coast of North America, when the continent, the supercontinent of Rodinia, broke up. The rock underneath it is the Middletown gneiss, and it dates back, as I said, to 1100 million, and that was put here at the time of the assembly of Rodinia. Now, it's high-grade metamorphic, and whether the composition of it tells you that it's a granite, because one of the few things that survives in metamorphism is the general composition of it. It may change completely in its mineralogy. It definitely changes completely in its texture. But aside from water and carbon dioxide, the general composition remains the same. And you can identify a granite that way, no matter what it's been through. Now, it could have been a rhyolite. That could have been rhyolite lava flows. It could have been rhyolite tuff. Or it could have been a granite batholith, crystallizing deep within the earth. It's been metamorphosed to a high enough grade that any textural differences are gone. But because it's granite in composition, and because there's so much of it, that is typical of a collision zone. So this was the collision that assembled Rodinia. So you've got both the assembly and the breakup recorded at this one outcrop, which is very nice. You can follow it up and down the east coast of North America, because the assembly of Rodinia in this area, at least in North America, pretty well paralleled the assembly of Pangaea. They assembled along the same line and then disassembled along the same line. The next time it happens, when Africa and Europe come together and squeeze out the Atlantic, which almost certainly will happen, will be a third time along pretty much the same line. If I'm wrong about that, sue me in another 300 million years. I won't worry too much about it. Okay, we've maybe got just time to go to the next stop, which isn't too far from here. We're going to cross North Mountain, which is